Hello, it's Benjamin Farland working on homework number 12, video problem number 3. The first thing you do for this type of problem is you create a free body diagram over to the left side, add all the forces, which is the 200 pound per foot distributed load from A to C over 6 feet. You also add the 600 pound point load on point D 3 feet after the distributed load, which is also 3 feet from the right side. You also add a reaction force going from the bottom of A, of the reaction A, and you also put a reaction force on B because it's a roller. A is because of it's a pin, B is because it's a roller. The next thing you would do is use the sum of the forces in the y direction to find that r of A plus r of B minus 600 minus 200 times 6 is equal to 0. And you will then be able to find that r of A plus r of B is equal to 1,800 pounds. After that, you can use the moment at B to find negative RA is times 12 feet plus 200 feet times 6 multiplied by 9, because that's the distance from the center of the distributed load to the B. And then you also add the 600 times 3 is equal to 0 to find that R of A is equal to 1,050 pounds, and we can put that back into the first equation we got up here of the R of RA plus RB is equal to 1,800 pounds. Once we do that, we find that RB is equal to 750 pounds. Once we find both of those, we can add lines all the way down to the bottom of the page on each point A, C, D, and B. And we can go over to the right side. Start from 0 up to X, including 0 up to X, not including 6. We create that section with A being on the right side and A being on the left side, O being on the right side. We put the distributed load in of 200 pounds per foot, and then we also put the reaction force on A of 1,050 pounds, and then we also put to the right side the shear force and the bending moment, and the measurement from the left, the A is measured as X. Once we do that, we can find the sum of the forces in the y direction equals 0, equal 1,050 minus 200 x minus 6. It's 200 x minus 6 because of the distributed load. Finding the midpoint between that and then minus V. Once we solve for V, we can find that V is equal to 1,050 minus 200x plus 1,200. And then we could also find that V is equal to a total of 2,250 minus 200x. At 0, the shear force is equal to 2,250. And at 6, the shear force is equal to 1,500. We can also find the bending moment using the sum of the moments at point O, where counterclockwise is positive. Sum of the moments is equal to 0, which is equal to the bending moment minus 1,050 times the distance x. It is negative because it's going the counterclockwise direction. And then we can also add the distributed load. It's going to be added because it's going counterclockwise around point O. And the distributed load is going to be 200 times x minus 6 as the load. And then we're also going to multiply it by x minus 6 over 2 to find the midpoint of that load. Once we solve for m, we can find that the bending moment is equal to 1050x minus 200x minus 1200 times x minus 6 over 2. To find that at x equals 0, the bending moment will be 0. And then to find that x equals 6, the bending moment will equal 6300. Next, we can go from including 6 to x, not including 9. We can then create the next section using the same philosophy as this diagram. Add the distributed load on top to the left side. Add the reaction force at A of 1050. And then we can also add the shear force and bending moment along with the x. We can do the sum of the moments in the y direction. Up is positive. Some of the forces in the y direction is equal to 0, which is equal to 1050 minus 200x minus 6 minus 200 times x minus 6, sorry, and then minus v, where again v is going to equal 2250 minus 200x, where at x is equal to 6 is 1050 and x is equal to 9 is 450. Sorry. And then I also forgot to mention earlier that after we do the sum of the forces to find v, and once we find v, we can go over to the left side, create a shear force diagram using each of the lines from A, C, D, and B. We can plot the first point of x equals 0 for 2250. We can plot x equals 6 as well. For x equals 6, shear force is equal to 1050. And then now we already have found the v for x equals 9 at 450. So we can plot that as well and create the line. And we could do the same with the bending moment. Go down further, create the graph for it. At x equals 0, the bending moment is equal to 0. X equals 6, the bending moment is equal to 6300. We draw the line there. And then at x equals 9, actually we have not gotten there yet. And for the bending moment for the second section is counterclockwise is positive. Sum of the moments at point O is equal to 0, which is equal to m minus the same 1050x for the reaction force at A. And that is going to be the same as well for the distributed load of plus 200 times x minus 6 times x minus 6 over 2, which will give us the same equation as the first time as well, of m equals 1050x minus 200x minus 1200 times x minus 6 over 2, to give us x equals 9 for the bending moment of 8,550. And then we can plot that point and continue the graph. And for the final section of including 9 to x to not including 12. Sorry. We can do the same, creating the section with the distributed load onto the top left side, the reaction force at A of 1050, and then we can also add the point load as D for 600 pounds. With the shear force going down, bending moment going counterclockwise. With x, we can do the same. Sum of the forces in the y direction, up is positive, is equal to 0. which is equal to 1050 minus 200 times x minus 6 minus 600 minus v, where v is equal to 1650 minus 200x. Where once we put x of 9 in, it becomes negative 150, so there's discontinuity there. It jumps from 450 to negative 150. And then we can also do the sum of the moments at point O, which is equal to 0, counterclockwise is positive, which is equal to m minus 1050x plus 200 times x minus 6 times x minus 6 over 2. And then we can also add 600 times x minus 9. Once we do that, we can have the equation equal to m of 1050x minus 200x minus 1200 times x minus 6 over 2 minus 600x plus 5400 is to where we put in x equals 12, we get 7200, and x equals 9, we get the same 8550. So we can plot the 7200 to finish the graph. I'm sorry. For when we put shear force at x equals 12, we get negative 750. We can plot that point and finish the line for the graph. After that's done, I need to find I need to determine the maximum bending stress at point C. So for that, I can take the stress of C is equal to mc over I, where C is equal to half of the height, and I is equal to the base times height cubed over 12, which is equal to 20 times 50 cubed over 12, which is equal to 208,333.3333 inches cubed. M at point C, if we can go look at the graph to where M at C is 6,300 pound-feet. And I convert that into pound-inches because I have inches cubed from my I value and also inches for my C value, which 63 pound-feet is equal to 6,300 pound-feet over 1 times 12 inches over 1 foot, which is equal to 75,600 pound-inches. And once I do the calculation for the stress at point C is equal to mc over I get 75,600 times 25 over 208,333.3333 to get the stress at point C is equal to 9.07 psi.